Okay, so we're going to go ahead and go through the answers for the waves worksheet. So make sure you check your work, especially before the test. And in this assignment round that we have, I've given you guys an optional review sheet that will be the same math problems with different numbers. So you can use this video to help you practice on the review before the test. Okay, so looking at the waves worksheet, we had 4 terms. I have a terrible printer right now. I'm almost out of ink, so bear with the missing spots in it. So we just wanted to know for each of the parts of the wave. So we did that in our notes the other day. Parts of the wave for number 1, you can tell that there is a distance they're measuring between 2 crests. We call that the wavelength. And also remember that we use the lambda symbol for wavelength. The second one, number 2, is showing us the rest position to the top of the crest. Rest to crest, or the height of the wave, is going to be our amplitude. Number 3 is the low part of the wave. The lowest part we call the trough. And the top of the wave, number 4, is what we call the crest. So that is a transverse wave diagram that we labeled the parts. Now, on a longitudinal wave, some people miss this. Label the wavelength on a longitudinal wave below. If you remember from the notes, it has to be the distance between 2 wave pulses or compressions, and it has to be the same point on each wave. So it looks like this wave is compressed to about here, and then there's a second compression over here. So I have to choose the same point. I can either start at the beginning and go from beginning to beginning, or I can go from end to end. Or if I want to go in the middle, I can go from middle, but I have to go to the same point of the middle of the next one. So I'm just going to choose towards the end, and I'm going to draw a little line over like this to the end of the second compression, and I'm going to label that with the lambda sign so I can label my wavelength on this longitudinal wave. Okay, so that is the wave diagrams. Now, the second part is the vocabulary. I have gone ahead and filled it out so I didn't have to do the whole thing with you while you're trying to listen to the video. So I'm going to get rid of a couple things so you can see. So the amplitude is G, the height of the wave. We just talked about that in diagramming the wave a second ago. The wavelength is J, which is the distance between 2 points on consecutive waves. And so remember, it could be crest to crest, or it could be from trough to trough, or if you have 2 identical points in the middle of the wave, it can also be that. So that is J. Crest is I, the highest point of the wave. Trough is H, the lowest point of the wave. Node is B, part of a standing wave that appears to be still. So if you remember in those standing wave video, it appeared that that part was still or not moving. And those are what we called the nodes. And those were along the rest line of the standing wave. Our frequency is K, which is the number of wave cycles per second. Period is A, the time it takes energy to travel 1 wavelength. So usually that's less than a second in most of our problems that we solve. And then wave speed is D, the distance a wave travels in a certain amount of time. So the distance would be in meters, the time would be in seconds. That would give us a speed of meters per second. Longitudinal wave is F, the energy travels parallel to the medium. So remember in this picture up here, the energy is traveling this direction. The medium, which happens to be the slinky, is also moving in this direction. So that is parallel. And then a transverse wave, which is C, is showing that energy travels perpendicular to the medium. So energy is traveling this direction, and the medium is traveling up and down. So that is perpendicular to each other. So that is the front part. So I'll hold that up there just for a couple seconds, and you can go back and look at it, and we're going to solve the math next. So on the back side is the math problems. So again, remember, if you are printing it and taking a picture, to make sure you show all work with units. And then if you are doing it on the document itself, typing into it, you still would need to show all the work with the units. So it's telling us that the frequency of the house current is 18 hertz, and they want to know the period of the house current. So we're looking for period. Remember, period is the time it takes to complete one wave cycle. That's it, just one. So that is this lovely equation that we did in our notes, which is, it's my doorbell ringing. The time, which is T, is 1 over frequency. So the only number we really need is frequency, which we're given. So we know that time, or the period of time, equals 1 over the frequency, which is 18 hertz. So we actually do have to get a number out of that. We could say it's 1/18th as a fraction, but that's not giving us a good time. So we want to do the division. We want to do the division that says 1 divided by 18, and that's going to give us a time in seconds. Notice it's a small amount of time, much less than a second there, because that's the time it takes one wave cycle to complete. So we're going to say that's 0.056. We'll go there. And that is time in seconds. So we're going to label it with seconds. Okay, the next one, the frequency of a stadium wave is 2 hertz. So we have a frequency and we have a wavelength of 10 meters. What is its speed? So remember, to find speed, we had 2 equations that we could look at. The first equation was a distance over time, which that's not what we're given. The second one is frequency and wavelength, which is what we were given. And according to this equation, speed equals frequency multiplied by wavelength. So we have all the stuff that we need for this one. So we have a frequency, a speed, and a wavelength that we need. So frequency is 2 hertz. Speed is x meters per second, because that's what we're looking for. And the wavelength is 10 meters. So we are going to do the equation speed equals frequency times wavelength. So x meters per second equals 2 hertz. And we're going to multiply that by 10 meters and get 2 times 10 equals 20 meters per second. Now remember, hertz is broken down into 1 over seconds. And we're multiplying that times a meter over 1 times a meter over 1. So that's where we get our meters per second for our speed. Okay, so an ocean wave travels at 20 meters per second. There's 4 meters between wave crests. What is the frequency? So in this case, we're given a speed and a wavelength. We're now looking for frequency. So we're still using these 3 variables. We just have to rearrange the equation. So our frequency is what we're looking for this time. So that's going to be x hertz. Our speed is given to us at 20 meters per second, and our wavelength is going to be 4 meters. So if we're looking at our original equation, remember we do have a circle that is speed on top, frequency, and wavelength on bottom. If we're looking for frequency, we're going to cover up F and get speed divided by wavelength. So it should be frequency equals speed divided by wavelength, and that's the equation we're going to use to find frequency. So we're going to do x hertz is our F, our frequency, equals our speed on top, 20 meters per second, and we're going to divide that by 4 meters, okay? And that is going to give us a 20 divided by 4, which is going to be 5, and since it's frequency, we're going to have hertz. Okay, 5 hertz. So the next one is a 2-part question. So we have, what is the frequency of a wave traveling 144 meters per second that has 600 cycles in 25 seconds? And also, what about the wavelength? So we're needing to find frequency and we're needing to find wavelength. We are given a speed, we're given number of cycles, and we're given 25 seconds. So let's start with frequency because we're given enough information to find the frequency based on the equation for frequency, which is frequency equals the number of cycles divided by time. So we have number of cycles and we have time. So frequency, number of cycles, and time are our three variable things that we are going to be looking for. X hertz is what we're looking for, frequency. We have 600 cycles. And we have that in 25 seconds of time. So our first equation to find frequency is going to be X hertz equals 600 cycles divided by 25 seconds. Oops, that's a C, not an S. Seconds. Okay, and then you're going to do 600 divided by 25. You could also look at it and say, how many quarters, 25 cents, are in $6? And you would do 600 divided by 25, and you would know that there are 24 quarters in $6. So you would have 24 hertz. That's going to be our frequency, but we're not done. It also asks for wavelength. So it says, what about the wavelength? So now remember, for wavelength, it's a measurement, it's a distance. We can use this circle up here to find wavelength as long as we had speed and frequency. Well, we have speed and we just found frequency. So now we have the ability to find wavelength. If we cover up wavelength, we get speed divided by frequency. So the equation will be wavelength equals speed divided by frequency. We have a speed, a frequency, and a wavelength. And we're looking for wavelength, so it's X meters. Frequency is what we just found, 24 hertz. And speed is 144 meters per second. So we go X meters, which is our wavelength, equals our speed, 144 meters per second. We're going to divide that by our frequency of 24 hertz. So when you do 144 divided by 24, you get 6, and that is meters. So 6 meters. I'm going to circle both the answers since this one happens to have 2 in it. Probably circle the rest of them up here too. Okay, so far we have found all the way through 19, so we're going to do number 20. So number 20 is, what is the wavelength of a wave? So we're looking for wavelength. And the wave travels 200 meters in 15 seconds with a frequency of 3 hertz. So now that we're looking for wavelength, we have a bunch of information to look through right now. And we have to figure out what is the actual information we need to find wavelength. So again, looking up at our circle up here to find wavelength, it's speed divided by frequency. We just did it in this problem here. So we need a speed and a frequency. We definitely have a frequency, but we do not have a speed. But we know that speed can be found in 2 ways. Okay, speed can be found by doing frequency times wavelength. Well, that's not helping us because we're actually looking for wavelength. Or speed is distance divided by time. And we do have a distance and a time given to us. So this order here is going to have to be solved for speed using distance and time, and then using the speed and frequency solve for wavelength. So to get speed, we need speed, distance, and time. X meters per second. Distance is 200 meters. Our time is 15 seconds. So that means that our speed, which is X meters per second, equals distance divided by time. So 200 meters is our distance. Our time is 15 seconds. It's a meter per second there. So 200 divided by 15. So you can 200 divided by 15, you're going to get 13.33333. So we'll just go equals 13.333 and that's going to be meters per second. So we're going to use that speed though. We need that speed to find wavelength. So this is the first answer that's going to lead us to find wavelength. So remember, we just did it up here. Wavelength equals speed divided by frequency. So we need a speed, a frequency, and a wavelength. Speed is what we just found. So we're going to have 13.33 meters per second. Our frequency is given to us right here, which is 3 hertz. And our wavelength is what we're looking for, which is X meters. And now we're going to plug it into this same equation we used up here. So X meters equals my speed on top, so 13.33 meters per second, and we're going to divide that by 3 hertz. So when I plug it in, you'll notice, whoops, I'll go this way. I'll just straight divide that by 3. Okay, and I get 4.444444. And I'll just plug it in this way so you can see. Same. And that is meters. We're looking for the wavelength. Okay, so this is the answer, the final answer that we were looking for. This answer was used to find that answer. Okay, how many wave cycles? So now we're looking for wave cycles are completed when a wave has a frequency of 45 hertz and 35 seconds. So in this case, this is the frequency equation that has number of wave cycles and time. So we had a circle, number of cycles on top, over top of frequency and time on bottom. So if we're looking for number of wave cycles, which we are, and we cover it up, we get frequency next to time. So that's a multiplication problem. So the equation we're going to use is number of cycles equals frequency multiplied by time. So we need to write out our variables, number of cycles, frequency, time. We're given a frequency of 45 hertz, a time of 35 seconds. So we're going to go number of cycles, which X doesn't really have a unit, remember? So we're going to do X equals frequency multiplied by time, so 45 hertz times 35 seconds. And then we're going to plug it in and go 45 times 35 equals 1,575 cycles. So it's 1,575 cycles completed when it has a frequency of 45 hertz. Okay, so that would be our final answer there. And notice the label isn't a unit. I just called it cycles because that's what it is. A sound wave has a pitch of 85 hertz. So it's frequency. Remember, frequency and pitch are related. We talked about this in the sound wave and the videos you had to watch. So when a sound wave has a higher frequency, it's going to have a higher pitch. So high F equals high pitch. And then on the opposite side, a lower frequency equals a lower pitch. Okay, so we've got to think about that when we're talking about frequency and pitch too. So we have this frequency of 85 hertz and a wavelength of 4 meters. We're looking for the speed of sound. We're looking for speed essentially, but because we're talking pitch and the frequency of sound waves, now we're going to talk about the speed of sound. So we are going to need the speed equation, which is the speed equals frequency times wavelength. So we're going to need a speed, a frequency, and a wavelength. Since we're looking for speed, X meters per second, frequency 85 hertz, wavelength 4 meters, X meters per second, don't know why I put that random equal sign there, equals 85 hertz times 4 meters equals 85 times 4 is 340. So we're saying the speed of sound is 340 meters per second. Now, if you remember doing the sound lab, the virtual sound lab with the trombone, they were using an average of 343 meters per second. It's about average sea level. So the slower it gets, typically you either change the medium it's traveling through, or if you go higher in altitude, like up a mountain, and the air is thinner up there, remember sound has to have a medium. That means it likes its molecules packed tightly, because then when the vibration energy moves from one molecule to the other, the faster it can reach the other molecules, the faster sound travels. If we spread out those molecules, that energy has to move farther to reach the next molecule to transfer the energy or the sound. Therefore, sound travels slower. So the higher you go up in altitude, the slower sound gets, because there's less air molecules packed tightly together. That's also why sound travels fastest in a solid. So we got to remember that. Okay, so last question. This says, hint, you need to use the answer from number 22. That was the one we just did. So that we're going to have to use this speed. So a sound wave has a pitch of 150 hertz. What is the wavelength? So now we're looking for wavelength, and we're only given frequency here, and then we have to use the speed of sound we just found right here. So speed, frequency, and wavelength. We're using the 340 meters per second we just found. And then we have a frequency of 150 hertz. And we're looking for the wavelength in meters. So we're going to find out soon if this is going to be a higher pitch or a lower pitch sound wave. So X meters. So since we're looking at wavelength, I'm going to jump up here to this circle. We're going to cover it up and get speed divided by frequency. So remember, wavelength equals speed divided by frequency. So X meters equals 340 meters per second that we just found. I'm going to divide that by my frequency of 150 hertz. Some of you might already be able to tell that this number is going to be different. So we are going to do 340, and we're going to divide that by 150, and that's going to give us a wavelength of 2.2, and since it's repeating sixes, I'm going to round it up to 7 meters. So here are the meters, or the wavelength. We already know it's 150 hertz, which is a higher frequency than this one. So therefore, we have a lower wavelength than this one up here. So remember, frequency and wavelength are inversely proportional. So as frequency goes up, wavelength would do the opposite and go down. That's what inversely proportional means. Or if wavelength went up, then frequency would in turn go down. So that's how they work out. And you can kind of see that in any diagram. You have a high frequency, here's your wavelength, it's short. You have a low frequency, here's your wavelength. Ooh, it's long. So inversely, and that was a question, proportional on that lab, the sound lab. Proportional, I probably should spell it wrong. Right, correctly. There we go. That's an R. There we go. Can't spell anymore. Okay, so that is the worksheet complete. Make sure that you check your answers from when you did the worksheet, and I would use the review to practice doing it on your own now that you've seen how to do it from me. Okay.